Here we got the x2 value is equal to 1.25. Then we put the value of x2 is equal to 1.25 in either A or B. So this is the equation A. Okay, so here we put the value of x2 is equal to 1.5. So we get is x1 plus 1.25 is equal to 5, and x1 is equal to 5 minus 1.25, which is equal to 3.75. So the first solution, which is continuous actually, we get is x1 is equal to 3.75, x2 is equal to 1.25, and z is equal to 5 into 3.75 plus 4 into 1.25. So we get z is equal to 5 into 3.75 plus 4 into 1.25, which is equal to 23.75. Now, the catch is that the equation, the z value that we get is 23.75, which is not integer, okay? x1 is 3.75, which is not integer. x2 is 1.25, which is also not integer. So here it becomes the first solution. Okay. Now this is the first node 1. Okay, z is equal to 23.75, x1 is equal to 3.75, and x2 is equal to 1.25. Now we will branch it into 2. Okay. Now here we have two variables. Both of them are continuous. The first one is x1 is equal to 3.75 and x2 is equal to 1.25. Now we will go for the greater one. x1 is equal to 3.75. Now for x1 is equal to 3.75, it has two boundaries. Okay, 3.75 is in between 3 and 4. So we can add, two boundaries to it. x1 is less than or equal to 3, it will cover this area, and x1 is greater than or equal to 4, so it will go for this area. So these two are the areas that we want to explore, and we will explore with the two branches that we made. Okay, now add this variable, this object actually constraint x1 is less than or equal to 3 to this branch, and put x1 is greater than or equal to 4 to this branch. Now here the objective function will become, it will become same, like it will not change, but the constraint will change. Now the first constraint is x1 plus x2 less than or equal to 5. The second constraint is 10x1 plus 6x2 less than or equal to 45. Here we will add this one and add it to here. x1 is less than or equal to 3. Now here we will have maximum z is equal to 5x1 plus 4x2 subject to x1 plus x2 less than or equal to 5 and 10x1 plus 6x2 less than or equal to 45. Now here the third constraint will be x1 greater than or equal to 4. You understand the branching method? Yes. So now we got the higher value. 3.75 is higher than 1.25. So we got the branching of x1 only. We didn't do it for x2. We did it for x1 only, because x1 is greater than x2 and is continuous, is in fraction or in decimal. Okay, the value is 3.75, so it lies between 3 and 4. So 3 and 4 are the boundaries for x1 here. So the first constraint that we add in first branch is x1 is less than or equal to 3. So it will cover this end of the constraint. And x1 is greater than or equal to 4, so it will go beyond 4 and cover this area. Now we will see if this branch or this branch yields some integer value or not. If any of this branch yield an integer value, it means that that branch is fathom. We are not going to branch it further. Okay, but if any of the branch doesn't yield integer values or doesn't go for optimal values, then we will need to branch it further and explore it further. But if the value we get here is less than the 23.75, okay, then we will not branch it any further. Okay, so that is how we do the branching. If against this branch we get the solution here, and for example we get the solution here is equal to 23 and we get 22 over here, it means that that one is okay. We will not further branch that. Okay, I will explain it when I will do the branching and find the solution for each branch. Okay, so now the branch 1, or we can say that LP2. Okay, we have x1 plus x2 is equal to 5. So for x1 is equal to 0, x2 is equal to 5, same like we did again. So I will not repeat it actually. I will just write it over here. Similarly, for the other constraint, 10x1 plus 6x2 is equal to 45. We got x1 Now we have another constraint, which is x1 less than or equal to 3. So we will convert it to x1 is equal to 3. Now we will actually graph it. x1, this is x2. Okay, this is 2, 4, 6, 8, and 10. We'll get 2, 4, 6, 8, and 10 over here. Okay, so the graph will be like more or less it will be same. Like it will get 5 and 5 over here. That will be for the constraint 1. For the constraint 2, we will have 4.5 over here, and we will have 7.5 over here, for example, and we will touch these two. Okay, now the third one is x1 is equal to 3. So it means that this one, now the intersection point has shifted over here. You see? Now this is the intersection point. The optimal solution has, shifted into this area. Now we will find the point of intersection and we will see what is the value of x1 and x2 in the branch 1. Similarly, we will do it for the branch 2 also, and we will compare it. I will dissect the page like this. Okay. Now Okay. Now here, to find the point of intersection, we have x1 is equal to 3. Putting x1 is equal to 3 in equation A, which is x1 plus x2 is equal to 5. We find that 3 plus x2 is equal to 5. x2 is equal to 5 minus 3, which is equal to 2. And z is equal to 5 into 3 plus 4 into 2, 15 plus 9 is equal to 23. Okay, so here x1 is equal to 3 and x2 is equal to 2 and z is equal to 23. Now what we see is that we produce the result x1 is equal to 3, which is integer, x2 is equal to 2, which is also integer. Okay, so this branch is actually fathomed. This is fathomed. We do not need to branch it further. We can say that this branch is fathomed and we do not need any further branching from LP2. Okay, so this branch actually LP2, this is fathomed. We do not need to further branch it. Now it has given us a benchmark. Z is equal to 23 over here, which is close enough to 23.75 that we got on the node 1, LP1. Okay, now we will see it for the LP3 and we will find the results. If these results are better, from this one, we will branch it. If these results are not better than this one, 23, if the result in LP3 is less than 23, okay, then we do not want to further branch it. But if it gives us more than 23, then we will go for the branching of it. Okay. Now, yes, so LP3 branch. Here we have x1 plus x2 is equal to 5 and 10x1 plus 6x2 is equal to 45, and we included another constant, which is x1 is greater than or equal to 4. You see here, now we will make another graph of it for this one, and we will see how it goes, what solution that does it offer to us. Now here we have 2, 4, 6, 8 and 10. Similarly 2, 4, 6, 8 and 10 over here. Okay, so x1 plus x2 is equal to 5. It will yield us 5 and 5. It will pass through 0, 5 and 0, 5. So these are the points that it will pass through. Now for the second constant, it will pass through 0, 7.5 and 4.5 and 0. So this is, for example, 4.5, 0, 0 and 7.5. So let's connect these 2 points. Now the third one is x1 is greater than or equal to 4. So converting it into equality, it becomes x1 is equal to 4. So now putting x1 is equal to 4, it will be somewhat over here. So now this is the point of intersection. To find the point of intersection, we need to put x1 is equal to 4 in equation A. Equation A is x1 plus x2 is equal to 5. So 4 plus x2 is equal to 5. x2 is equal to 5 minus 4 is equal to 1. So this point of intersection actually yield x1 is equal to 4 and x2 is equal to 1 and z is equal to 5 into 4 plus 4 into 1, which is equal to sorry. Point of intersection is actually somewhat okay. Let's put it into equation B. We see that 10 into 4 plus 6 into x2 is equal to 45. So 6 into x2 is equal to 45 minus 40. 6x2 is equal to 5. X2 is equal to 5 by 6, which is equal to 0.83. X2 is equal to 0.83, not 1 actually. The reason is that if we put here, if we put x1 is equal to 3 and x2 is equal to 2, it satisfies the constraint 2. But if we put x1 is equal to 4 and x2 is equal to 1, it does not satisfy this second constraint. So in order to find the point of intersection, it must satisfy both the constraints. Okay. So x1 is equal to 4 and x2 is equal to 0.83 and z is equal to 5 into 4 plus 4 into 0.83. So it will give us 20 plus 3.33. 4 into 0.83 is equal to 3.32. 23.32. Now the catch is that this solution is actually better than this one. It is giving us 23 and this branch is giving us 23.32. It means that we need further branching. We can explore it to find the new optimal. Okay. This is optimum, but not optimal. It's not the final solution. It is better, but not the best one. Okay. And now we need to explore this one, further branching. We will do further branching of this one. We will branch it further. Now here, x1 is equal to 4 and x2 is equal to 0.83. Okay. Now we know that x1 is equal to 4 is an integer. Okay. x2 is equal to 0.83 is not an integer. So 0.83 lies between 0 and 1. This is 1 and this is 0. 0.8 is somewhere over here. So x2 is less than or equal to 0 and x2 is greater than or equal to 1. These will be the two other constraints that will be added on this branch and this branch respectively. Are you understanding the problem? Please let me know where. Yes, you have to do it. If not graph, you can just find the point of intersection directly. But graph is better because it will give you like somewhat idea where the points are intersecting. Okay. Now here on this branch, this is LP4. This is LP5. So LP4 will add another constraint which is x2 is less than or equal to 0. Okay. And here at LP5 it will add x2 is greater than or equal to 1 as another variable. Now we have four variables at LP4 and four constraints at LP4 and four constraints at LP5. On the first node we had only two constraints. Then on the branching we had 3 and 3 at both sides. Now at LP4 and LP5 we have 4 and 4 constraints. Okay. Now solving it for LP4 and LP5. Okay. For LP4 we have x1 plus x2 is equal to 5. 10x1 plus 6x2 is equal to 45. x1 is equal to 3 and x2 is equal to 0. And at LP5 we have x1 plus x2 is equal to 5. 10x1 plus 6x2 is equal to 45. x1 is equal to 4 and x2 is equal to 1. Okay, so these are the constraints actually that we need to solve the equation for. Okay, so now here we will make x1 and x2. Okay, to find the point of intersection, we have like let's put x2 is equal to 0 in B. 10x1 plus 0 is equal to 45. x1 is equal to 4.5. Now putting x1 plus x2 is equal to 5. Okay, sorry. The z value is 5. x1 plus 4x2 implies that z is equal to 5 into 4.5 plus 4 into 0 is equal to it will give us 4 5 for 20 and 5 for 25 2.5, so 22.5. Z is equal to 22.5. Okay, now for this one, putting x2 is equal to 1 and putting into equation B, we get 10x1 plus 6 into 1 is equal to 45, plus that 10x1 plus 45 minus 6, 10x1 is equal to 3.9. Let's see if x2 is equal to 1 satisfy all others. But x1 is equal to 3.9, it is not greater than or equal to 4. So this value is not satisfying that constraint. It will go towards infeasibility because it is not satisfying any of the constraints. x1 is equal to 3.9, it is directly not satisfying constraint 3 because constraint 3 is x1 is greater than or equal to 4, and here x1 is 3.9. So it is not satisfying this constraint. Now we will go for the it will become infeasible because it is not satisfying the constraints x1 is greater than or equal to 4. Okay, so LP5 will be infeasible. It is not yielding any feasible solution. And the reason is that for x2 is equal to 1, we get x1 is equal to 3.9. But here we have a constraint that x1 is greater than or equal to 4. Okay, and it is not satisfying that constraint because this value is less than 4. So it will give us an infeasible solution. So we do not need to branch it. It is also fathomed. You want to ask something? Yes, it is fathomed. You see that for x2 is equal to 1, if we put it in equation B, it gives us 3.9 value, but x1 is greater than or equal to 4. That is the constraint over here. And it is not satisfying that constraint. So it becomes infeasible. And so it is also fathomed because it is not giving us any feasible solution. So now we will branch. This is 22.5. Okay. So we will branch this further because we are not getting the integer solution of it because we have 4.5 x1 is equal to 4.5 and x2 is equal to 0 here. So we will further branch it. Now 4.5 is actually lying between 4 and 5. So x1 less than or equal to 4 and x1 greater than or equal to 5. Let's put these two constraints in this and this branch and see how it goes. So here x1 is less than or equal to 4 and here x1 greater than or equal to 5. I will solve it for LP6 and LP7. and see how it goes. Now here we have x1 plus x2 is equal to 5 and 10x1 plus 6x2 equal to 45, and also we have x1 is equal to 3 less than or equal to 3, sorry, greater than or equal to 3, LP4, LP2, LP3. Yes, and x2 equal to 0. But the 4 constant, yes, equal to 0. And now we have x1 less than or equal to 4. If we put x1 is equal to 4, making it equality, x2 is equal to 10 into 4. But here we also have like x2 is equal to 0. So x is 0. Actually, yes. If we put x1 is equal to 4, like we equate it to 4, then x2 is equal to 0. It is also a constraint because it is less than or equal to 0. So we will equate it to 0. So x1 is equal to 4 and x2 is equal to 0. And z value we get is 5 into 4 plus 4 into 0, which is equal to 20. For LP7, we have x1 plus x2 is equal to 5. Then x1 plus 6x2 is equal to 45. x1 greater than or equal to 4. x2 greater than or equal to 1. And now x2, x1 less than or equal to 4. Now we see that we have x1 is greater than or equal to 4, and here x1 is less than or equal to 4. Both of these contradict, so it will not give us feasible solution because the constants are contradicting each other. We have x1 greater than or equal to 4 and x1 less than or equal to 4. So both are these are contradicting each other. So we are not getting any feasible solution. So it is fathomed. But here we get a solution for this is also integer and this is also integer, and we get 20. Now here we need to stop. Why? Because we got all integer solution. Okay. Now out of all these, we see that the final solution we get was 20 over here. It was infeasible. LP4 we got 22.5. Okay. And before that, in branch 1, we got integer solution which was equal to 23. So this 23 is the maximum that we can get through integers. Okay. So this is the optimal solution. and this is the lower bound. This 20, this one is the minimum feasible solution that we get through integers, and this one is the maximum that we can get through integer programming. So this is the optimal solution. This is optimum, but not optimal. And this is the lower bound of it. 20 is the lower bound, and 23 is the upper bound or maximum that we can get. I will also do another example of it after the break. I will, I will do another example, and if you have any, kind of problem understanding it, it will get clear. Okay, because this is kind of, an iterative process. Iterative branch and bound is also iterative process, just like simplex. You need to repeat the procedure again and again to find the optimal solution. But the thing is that you need to know the fathoming of it, like, the branching of it, adding another constraint to it, which variable to pick among the two if both of them are in fraction form, like just we did it in the branch one, because in branch one we had like x1 is equal to 3.75 and x2 are 1.25. So 3.75 was greater than 1.25. So we got x1 is equal to 3.75 as the branching variable, and we made the branches based on x1. So these are the points. Yes. Okay, in the two-phase method, actually, in the big M, we just started with we started with Z and ended with Z. We solved all the equations for Z optimal value, just like you practice. For example, we had like a maximum Z is equal to 5x1 plus 4x2. Okay, so in M method, we solve it directly for Z, but in two-phase method, we first solve it for the R, the artificial variables. Then after solving it for R, we introduce, substitute actually the R values into another simplex W, and we find the value for Z. These are the points that you need to understand. So should I write it somewhere? You got my point, or you are still confused about it? Okay. For example, in big M method, we have like maximize Z is actually, it is actually an algorithm. The difference between a simple method and algorithm is that algorithm has a set of procedure. It has a distinct set of procedures or steps that you need to follow and repeat it again and again. You do not skip any of the, any of the step. You follow each and every one, and you do the basic method, and you receive or you find the solution of the problem. So branch and bound is actually an it is an iterative method or algorithm for integer programming problems. It deals with the integer programming problems. Okay, and it has a distinct set of steps. Okay, the first one, it is a basic distinct uh, distinct steps are three. The first one step is to relax ILP and transform it into uh, simple LP. Okay. The second step is to solve the linear programming problem, and the third one is to reintegrate integer constraints and see if solution is arrived. If the solution is arrived, it is fathomed. If it has infeasible solution, it is fathomed. And if the solution is lower than the lower bound, it is also fathomed. So the fathoming has three conditions that need to be met. Okay. So now this is the basic branch and bound. I will do another example on it. So that we can, get an idea of complete idea of a branch and bound. So now the second example I will do, it is from another book. I will send you the book if you want me to send you, or I can send you just the snapshots of it. Okay. So it is the Tefla Corporation, which makes chairs and tables. Okay. And each table requires 1 hour of labor, and it requires wood of each table requires 9 square feet of wood, and each chair requires 1 hour of labor, and each chair requires 5 square foot of wood. Now, the total labor hours available is equal to 6, and total wood available is equal to 45 square feet. Now you can see that this is a kind of problem in description. We will use the description to make a mathematical model of the problem, and then we will use the branch and bound method to find the number of chairs and tables that need to be made in order to satisfy the constraints and maximize the profit. Now the profit per chair is $5, and profit per table is equal to $8. Okay, so I will need your input to find the objective function of it. We have profits over here, so it is uh, maximization Z, and it is let x1 is equal to tables and x2 is equal to chairs. So it will be equal to 8x1 plus 5x2. Subject to, now each table x1 requires 1 hour of labor and each chair also require 1 hour of labor. So 1 x1 plus 1 x2 is less than or equal to the total labor hours available are 6 hours. So this is the first constraint and this is the time or labor hour constraint. Now the second constraint is the wood constraint. Each table requires 9 square feet of wood and each chair required 5 square feet of wood. So we can say that 9x1 plus 5x2 is less than or equal to, and the total wood that we have is 45 square feet. So it is 45 square feet. So this is the wood constraint. Okay. And the additional constraint over here is that x1, x2 must be greater than or equal to 0 and x1, x2 belongs to integers. Both of them are integers. The first thing that we will do in the branch and bound method is to remove this last one, the integer boundness of it. So first of all, we will reduce it to the normal. The first step is relaxing. So x1 plus 5x2 subject to x1 plus x2. Five x2 is less than or equal to 45 and x1 x2 greater than or equal to 0. So we removed the integer constraint of it and we will solve it using the normal graphical method. Using graphical method. So the first constraint is x1 plus x2 is equal to 5. We will equate it to 0. X1 is equal to 5. 5 0 that we get 0 5 and 5 0. These are the 2 points for this constraint. For the second constraint we have 9x1 plus 5x2 is equal to 45 implies that x1 is equal to 0, x2 is equal to 45 by 5 is 9, and for x2 is equal to 0, x1 is equal to 9 5 or 45, so is equal to 5. So we have 0 9 and 5 0 the other points. Now we will graph it like we do it in graphical method. So here we say that we have 2 4 6 8 10 and 12. Here 2 4 6 8 10 and so on. So the first point is 0 5 and 5 0. So here 0 and 5 and 5 and 0. So we will, this is the first constraint. The second is 0 9 and 5 0. So for x1 is equal to 0, x2 is equal to 9. So this is the point 9. And for x2 is equal to 0, x1 is equal to 5, which is exactly this point. So here Okay, now this one, no, the intersection is just like over here. The intersection is over here in the xy plane, so it is not infeasible. If the intersection were somewhat over here or here, then it would be infeasible one. Oh, sorry, this one. This is feasible. This constraint is not equal to 5, it is actually 6. We wrote it wrong. There are 6 labor hours actually available. This is 6, 0, 6, and 6, 0. This is actually the point. Okay. Now we need to see this point of intersection to find the optimal. Okay. Now to find the point of intersection, we use both of these constraints. X1 plus x2 is equal to 5 and 9x1 plus 5x2 is equal to 45. If we multiply this by 9, what we will get is 9x1 plus 9x2 is equal to 45. Now, and if we subtract the, it is 6, 9, 6 are 54. So it will get us 9, it will be cancelled, and it will be equal to 4x2. So x2 is equal to 9 by 4. Okay, now we have x2 over here. Now x1 plus x2 is equal to 5. If we put x2 is equal to 9 by 4, we get 5 minus 9 by 4. If we get the LCM of it, we will get 4, and it will be 20 minus 9, which is equal to 11 by 4. So, okay. Okay, so now we have x1 also in decimal and x2 also in. Okay, we got both in decimal. So now from here it is the node 1 is the upper bound. I will say the upper limit to address here is z is equal to 8 into x1 it will get us 55 divided by 4, 11 point. So this is the maximum that we can achieve. This is the maximum that we can achieve. Okay, this is the upper bound. Calculate the lower bound and the optimal value for the integer. So in order to get the, uh, we will the maximum of these into the lower limit and upper limit, and we will put the lower limit. Now is okay. Okay, so if you have any question up till now, you can ask me. What we did was we first changed it from integer to the continuous one, the simple LP. We solve it using the graphical method, and we found this intersection of it to find the best z that we can get the upper bound and x1 and x2 using these two constraints. If you have any question, you can ask me now so that I can proceed now. Okay. The next step is the next step is to branch it. Okay. Now we have x1 is equal to 9 by 4 and x2 is equal to 11 by 4. We see that x2 is equal to 11 by 4 is greater than x2 is greater than x1. So we will branch x2. Okay. Okay. Now branching x2, it will get us 11 by 4 actually means we have a value of 2 point something. Okay. Now 2 point something lies between 2 and 3. Okay. So x2 less than or equal to 2 and x2 greater than or equal to 3 to cover this area and this area. Okay, because we do not need this one. We do not need the in-between area. We need this area either or this area to find the integer solution of it. The LP2 to LP3, it will be added x2 greater than or equal to 3 and here x2 less than or equal to 2. Okay, these are the additional ones. Okay, now solving it for the LP2, where we have an additional of x2 is equal to 2. Here, for x2 is equal to 2, now you can see it. Can you see it now? Let me open it again. Can you see it now? Oh, okay. Because now we have x2 is equal to 2. x2 is equal to 2 lies over here. So we will have a cut over here. Okay. Now the point of intersection is somewhat over here for three constraint, and the second point of cut is over here. So the z will most probably lie over here. Okay. Now for x2 is equal to 2, let me calculate the value of z, x1 and x2. If x2 is equal to 2 is added. Okay. Now if we add x2 is equal to 2, then the value of x1 is equal to, let me add 9 into x1 plus 5 into x2 is equal to 45. Now x2 is equal to 2, so 9 x1 plus, yes. Okay, we can do that. No problem. Okay. Most probably after like 20 minutes, maybe the results are good. Okay. Yeah. Let's log in like after 20 minutes. Okay. Previous question. Actually, here we had a problem. Maximize z is equal to 8x1 plus 5x2 subject to x1 plus x2 less than or equal to 6. 9x1 plus 5x2 is less than or equal to 45. So first we solve it graphically, and from the graphical method we came to know that the optimal x1 and x2 are x2 is equal to 9 by 4 and x1 is equal to 15 by 4. Okay, and the z value is 41.25. So this is the maximum z value. This is the upper bound. This is the maximum z value that we can actually achieve. Okay, now after doing this, here we have z is equal to 41.25. This is the x1 value, this is x2 value. Now we know that x2 is equal to 2.25 and x1 is 3.75. So x1 is greater than x2, so we will branch it based on x1. Okay, now x1 is equal to 3.75, so it lies between 3 and 4. So 3 is the lower limit and 4 is the upper limit. So we branch it according to these limits. X1 is less than or equal to 3 and x1 is greater than or equal to 4. Because we are already in this region between 3 and 4. We either go this side or we either go at this point. Okay. So now here we create two subproblems from the x1, the branch 1, which is LP2, and the branch 2, which is LP3, which is subproblem linear problem 3. Okay. Now here we add x1 is less than or equal to 3. This one is added into these constraints. And here we add x1 is greater than or equal to 4 and put it over here. Now we solve it for this and also for this. And if any of it, give us an integer value for x1 and x2, we call it fathom and we just stop the branching from that node. And if any of this give us like decimal values or fractional values, we are going to branch it from that point, from that node. So now here at this point, x1 plus x2 is less than or equal to 6, 9, x1 plus 5, x2 is less than or equal to 45. We add another constraint, x1 is less than or equal to 3. So now for here we equate, we already have modeled both the upper two constraints, but this one is the new constraint. And upon equating it to the right hand side, we found it as x1 is equal to 3. So if x1 is equal to 3, x2 needs to be found. Now putting this is A, this is B, and this is C now. So putting in A or B, we get, for example, we put in B here, we get 9 into 3 plus 5 x2 is equal to 45. So 9 3 27 plus x2 is equal to 45. So 5x2 is equal to 45 minus 27, which implies that x2 is equal to 45 minus 27 divided by 5. So it will give us 18 by 5, which in turn give us 3.6. Now we see that x1 is less than or equal to 3 and x1 plus x2 is less than or equal to 6. Now if we put x1 is equal to 3 and x2 is equal to 3.6, it does not satisfy this constraint. So it cannot be 3.6. Okay, here it fails. We need to find the exact value of x2 that satisfies all these constraints. So now if we put x1 is equal to 3 in A, we get 3 plus x2 is equal to 6. Implies that x2 is equal to 6 minus 3 is equal to 3. Now x1 is equal to 3 and x2 is equal to 3. These satisfy both the constraint, this one as well as the first one and the third one. So we have 3 value over here and z value is z value is 8 into x1, which is 3 plus 5 into 3, 24 plus 15 is equal to 39. Now here we got 39 and we got x1 is equal to 3 and x2 is equal to 3, which are both integer. So this is fathomed because we got integer solution. Now this is a candidate solution, but we need to explore the other nodes too. Okay, this is the candidate solution. If it does not give us the another solution, this is going to be the optimal solution. But let's see what does this tree give us. Okay, now upon doing this, for example, we put x1 is equal to 4, then what will be the value of x2? The value of x2, put x1 is equal to 4 in B. So 9 into x1 plus 5 into x2 is equal to 45. Now x1 is equal to 4, so 9 into 4 plus 5 x2 is equal to 45. This gives us 36, so 5x2 is equal to 45 minus 36, which in turn give us x2 is equal to 9 by 5. And 9 by 5 is equal to 1.8. Now, for this, the z value is equal to 8 into 4 plus 5 into 1.8. Thirty-two plus 5 into 1.8, it will give us 941. Z is equal to 41. Now we see that here we got 39 and here we got 41. It means that it is somehow giving us some better solution. But still x2 is equal to 1.8, which is in fraction. So we must, divide it into further two trees. The first one, and it will be based on x2 make two trees. Okay, the first one will be, as it is 1.8, so it is between 1 and 2. So x2 is less than or equal to 1 and x2 is greater than or equal to 2. We must add x1 less than or equal to 1 into this tree and x2 greater than or equal to 2 into this one. Now the total number of constraints here in LP4 will be x1 plus x2 is less than or equal to 6. 9x1 plus 5x2 is less than or equal to 45. x1 is greater than or equal to 4 and x1 is less than or equal to, x2 is, this is x2, this is not x1. x2 is less than or equal to 1. These are the four constraints. And here in LP5, which is sub-problem of LP3, we have x1 plus x2 less than or equal to 6, 9x1 plus 5x2 less than or equal to 45, x1 is greater than or equal to 4, and x2 greater than or equal to 2. Now we will solve both of these trees and we will see which one gave us a better solution, which is better than this 39. And still it is, the integers. So we are in search of the integer solution actually. So here what we get is LP. We will first explore the LP4. Okay, so in LP4 we have x1 plus x2 less than or equal to 6, 9x1 plus 5x2 less than or equal to 45, x1 is greater than or equal to 4 and x2 is less than or equal to 1. Now let's x2 is equal to 1. Okay, then we see that x1 is still to be found. Now if we put x2 is equal to 1, okay, and putting it into 9x1 plus 5x2 less than or equal to 45, we get 9 into x1 plus 5 into 1 is equal to 45 implies that 9x1 is equal to 45 minus 5. Dividing both sides by 9, we get x1 is equal to 40 by 9. And 40 by 9 will give us 4.44. Okay. Now we have a constraint over here that x1 must be greater than 4. So it is satisfying that condition. Okay. It is also satisfying this one, and it is also satisfying the first one. Okay. So this is the legit value for x1 is equal to 4.44 and x2 is equal to 1. Now the z value over here is 8 into 4.44 plus 5 into 1. It will give us 35.52 plus 5, 40.52. Okay, now this is the solution that is given by the LP4. Now let's explore the LP5 and then come to the LP4 again and see if LP5 give us some competent solution. Now doing it for LP5, here we have x1 plus x2 less than or equal to 6, 9x1 plus 5x2 less than or equal to 45, x1 is greater than or equal to 4, and x2 is greater than or equal to 2. Okay, I just wrote this LP5 problem over here and let's solve it. For example, x2 is equal to 2. I equate x2 greater than or equal to 2 to 2. Okay, now what is the value of x1 over here? Okay, now putting it in equation B, we get 9 into x1 plus 5 into 2 is equal to 45. So 9x1 plus 10 is equal to 45, and 9x1 is equal to 45 minus 10. Dividing both sides by 9, we get x1 is equal to 35 by 9, and it gives us 3.88. Now x1 is equal to 3.88. Okay, and we have a condition that x1 must be greater than or equal to 4. So it is less than 4. So it will give us infeasible solution. Okay, so it is also fathomed. You understand it? So this LP5 node is also, it is fathomed. Now we have only LP4 to get explored. Now the LP4 will be converted, it have two trees. Okay, now here x2 is equal to 1, but x1 is equal to 4.44. Okay, so we will branch it according to x1. Now the x1 is between 4 and 5. So x1 is less than or equal to 4 and x1 is greater than or equal to 5. We will put x1 less than or equal to 4 in this branch, which is LP6, and in LP7 we will put x1 is greater than or equal to 5. Okay, so now here the number of constraints are x1 plus x2 less than or equal to 6, 9x1 plus 5x2 less than or equal to 45, x1 is greater than or equal to 4, x2 is less than or equal to 1, and I will also add this one, x1 is less than or equal to 4. Now here x1 plus x2 is less than or equal to 6, 9x1 plus 5x2 is less than or equal to 45, x1 is greater than or equal to 4, x2 is less than or equal to 1, and x1 is greater than or equal to 5. Now we see that x1 is greater than or equal to 4 is here, and we also add x1 is less than or equal to 4. So both of these constraints contradict each other. So it will also give us infeasible solution. So it is also fathomed. This node, this is x1 is less than or equal to 4, and we already had x1 is greater than or equal to 4. So both of these constraints contradict each other. So this is also infeasible, and this branch is fathomed. Now we have only LP7 left. Okay. Now let's put x1 is equal to 5, because we have the newest constraint over here, x1 is greater than or equal to 5. So we put x1 is equal to 5. Then x2 needs to be found. Now for x2, we have 9x1 plus 5x2 less than or equal to 45, which means that 9 into 5 plus 5x2 is equal to 45, implies that 45 plus 5x2 is equal to 45. So 5x2 is equal to 45 minus 45 is 0. So x2 is equal to 0 divided by 5 is equal to 0. So here x1 is equal to 5 and x2 is equal to 0. The z value is equal to 8 into 5 plus 4 into 0. It will give us z is equal to 40. You understand this point? Okay. So now let calculate the whole scenario. For the first one, that we removed the integer programming constraint, we got 41.25. So this is the maximum that we can get. Then the subproblem 1, which was LP2, we got 39, but we got integer, so this is not to be mentioned over here. In this one, subproblem 3, which is LP3, we got z is equal to 41, but we got x2 is equal to 1.8, which is also non-integer. So that is also, neglected. Here in LP4, we got z is equal to 40.5, but x1 is 4.44, which is also a non-integer. So we also neglect it. In LP5, it is fathomed because it was infeasible. LP6 was also fathomed because it was infeasible. Only the LP7 we got both x1 and x2 as integers. X1 is equal to 5, x2 is equal to 0, and z is equal to 40, which is close to 41.25. So this is the best solution, integer solution actually. This is the best integer solution. And for that, x1 is equal to 5, x2 is equal to 0, and z is equal to 40. Now you understand the branch and bound? Okay, so that is how the branch and enumeration. Okay, now this implicit enumeration, it actually has two terms. Okay, well, the first one is implicit and the other thing is enumeration. So implicit is the opposite of implicit is explicit actually. So explicit is mean that you do all the things, you find all the things, all the solutions. In implicit, we leave some solution, or we do not explore all the solutions. Okay, and the basic method is enumeration method. So enumeration basically it is a systematic approach, or you can say methodology, to find all or some of the possible solutions to a problem set. For example, we have a problem, so we go into the problem and we solve it for different solutions. We solve it for different combinations of in all in operation research. Actually, in OR, we have different variables actually. Okay, so we have a number of combinations of solution possible. Exploring these solutions or combinations refers to enumeration. So basically, implicit enumeration is a systematic approach or a methodology to find some or all of the feasible or basic solutions to the problem set actually, and it is all about exploring and counting the solutions step by step, making trees, and finding the feasible solution and non-feasible solution, blocking the tree on lower bound and non-feasible solution, and exploring it further on some feasible solution that we find out in the middle of the problem. Okay, so this is the implicit enumeration. In nature, actually, it resembles to the branch and bound method because we also use branching in enumeration. We use branching in implicit enumeration. And the most important thing that makes it different from the other processes is that, i.e., I will refer it to as i.e. implicit enumeration, it is used for 0-1 problems or binary problems. So this is the most important part of it, that implicit enumeration is used for binary problems only. It is not used for any integer problems or mixed integer problem. It is used for the binary problems only. Okay. So the basic method is that we find a node, for example, node 0. Okay. We then branch it for certain value of, for example, here I take x1. Okay. Now we explore two values of x1. x1 is equal to 1 and x1 is equal to 0. And for example, we have a problem that has like three variables, x1 plus 5x2 plus 3x3. Okay, now we have three variables. Okay, so now at this node, actually, it will transform into 2 and 3. Okay, and we will fix x1 in this at this 2 node 2 and node 3. Actually, x1 will be fixed variable while x2 and x3 will be free variable. Let me introduce the concept of fixed and the free variables. The fixed variables are those which have attained certain value. For example, we fix the value of x1 is equal to 1 over here, and we fix the value of x1 is equal to 0 in this branch, in node 3. So x1 is actually fixed in both these branches. But we do not have any specific value for x2 and x3 in either node 2 or node 3. So x2 and x3 on node 2 and node 3 respectively are actually free variables. So what we do is we fix one variable and find another variable, the values for another variable for which the equation, for example, we have two constraints for which both the constraints are true, which satisfy both the constraints. Okay. So if it does not actually satisfy the constraint, then we find the feasibility of it. Using certain table, I will make that table over here. We use that table to find the feasibility for that variable, that specific variable. And if that is true, then we branch that variable out and fix the value of this next variable. For example, here we have like x1. Here we actually fix x2 is equal to 1 and x2 is equal to 0. So now at node 4 and node 5, actually, we have two fixed variables. So fixed variables over here will be x1 and x2, and the only free variable over here, it will be x3. X3 can attain either value 0 or 1. Okay, and we then explore node 2, node 4, and node 5 over here. So this is the basic concept of implicit enumeration. We use the branch and bounding method actually, but it is not in integer form. It is used in binary form. Like here, like in the branch and bound method, we actually, for example, if the value was like 0.9, so we fixed it between 0 and 1, and we used x2 is less than, for example, this is x1. X1 is less than or equal to 0 and x1 is greater than or equal to 1. But here, this concept is not used. We have only two values that each of the variable can attain. It is either 0 or it is 1. It means that it can be used for project selection, for the company expansion problems, and these kind of problems, in which the decision variables either attain a value of 1, for example. So it means that that project is selected, and it can attain either value of 0. It means that that project or product is rejected. You understand the concept of the implicit enumeration? Okay. So now I will go towards a certain problem, and I will explore all these things one by one in each of the iteration. Actually, this is an iterative process. Okay. For example, in iteration 1, we fixed x1. In iteration 2 or t2, we fixed x2 or x3. You can, pick it arbitrarily. You can pick either, for example, if we have like 5 variables, okay, so I can pick like x5 on the first. I can pick here x5 and not x1. I can pick x2 as well. I can pick x3. But we go for with the sequence. So I will go for x1 and then x2, x3, x4, and in the last I will go for x5, and we will see which of the node actually gives us a proper feasible solution and which of the nodes are kind of fathomed because of the non-feasible solution, or certain kind of, we'll deal with the problems like if it has infeasible solution, or it does not satisfy any of the constraint. So we will block it over there and we will not explore that node further. That node will be left as it is, just like we did with 3 over here. 3 is unexplored over here. but 2 has an extension of 4 and 5. So that is how it is done. I will do a problem, and inshallah you will understand the whole concept of it. Okay, but before going into the problem, let me make a table on which we will work regularly during the solution of the problem. Okay, so now we have a problem over here. The problem is maximize z is equal to minus 7x1 minus 3x2 minus 2x3 minus x4 minus 2x5. Subject to, we have 5 variables over here, okay? x1, x2, x3, x4, and x5. And subject to minus 4x1 minus 2x2 plus x3 minus 2x4 minus x5 less than or equal to minus 3. And the other constraint is minus 4x1 minus 2x2 minus 4x3 plus x4 2x5 less than or equal to minus 7. So let's name it A and name the other constraint is B. Okay, and x1, x2 up to x5 actually belongs to 0, 1 class. It means that they are binary. Now, at the start of this game, actually, we have, let's understand that at node 0, actually, or node 1, at first node, we have all variables x1, x2 up to x5 are free variables. None of it is fixed. Okay. Now, the best completion at node 1 is actually putting x1 is equal to x2 is equal to x3 is equal to x4 is equal to x5 is equal to 0. If you put all of these equal to 0, this is the best completion of the problem at node 1. It is the lowest that we can get actually. Okay, so for all these values, put the above values in A and B to see if it satisfies the constraint. Okay, so we put, this is constraint A, minus 4 into 0 minus 2 into 0 plus 0 minus 2 into 0 minus 0 is less than or equal to minus 3, which is 0 less than or equal to minus 3. So it is not true. Now, constraint B, we have minus 4 into 0 minus 2 into 0 minus 4 into 0 plus 0 plus 2 into 0 less than or equal to minus 7. So it will give us the left hand side will give us 0 less than or equal to -7, which is also not true. Okay, so the solution is not feasible at x1 is equal to x2 is equal to x3 is equal to x4 is equal to x5 is equal to 0. So at this initial values that we got over here, the solution is actually not feasible. So now we will check for the feasibility of it. But to check the feasibility of it, we must know about a certain table. Okay, so this is called feasibility table. Now this is the type of constraint. Okay, this is the sign of free variable in constraint. Okay, and this is the value assigned. Okay, now the type of constraint can either be less than or equal to, less than or equal to, greater than or equal to, or greater than or equal to, and the sign will be plus minus. Like here, -4, we have here less than or equal to, and the sign for the coefficient of x1 in B is minus. Okay, so here it is plus minus and plus minus, and the values that it can attain is 0, 1, 1, and 0. So this is the important table that you need to understand in order to check the for feasibility. Now, checking feasibility points. Here, this is a part of the algorithm actually. I didn't put it. It will be given to you. I, yeah, this table will be given. Yeah, this is the part of the this method. I didn't do these values. These are given by the the person who have discovered this, actually the implicit enumeration method. I will make use of it, then you will understand it. No, these are fixed. These are fixed. If we have like less than or equal to a constraint and the sign of the free variable in constraint is positive, we assign 0 value to it. Okay. Now checking feasibility at node 1, we have the first constraint is -4, -2, plus 1, -2, -5, -1 is less than or equal to. Okay. So now we can say that in A, okay, in A, like in first constraint actually, x1 will be equal to, x2 will be equal to, x3 will be equal to, x4 will be equal to. I'm making it blank, just to engage you in the process. Okay, for x1 here we have in the A we have -4, so the sign is minus, and the constraint is less than or equal to. So here we can see this is less than or equal to, this is also less than or equal to, and this is the sign for the free variable. This is plus, this is minus. So for x1 we have sign is equal to minus, so the value it will get is 1. So x1 will be 1. For x2 the sign is negative, so same, it will be also 1. For x3, the sign is positive. It is less than or equal to sign is positive. The value assigned will be 0. For x4, it is negative, so it will be 1. And for x5, it is also negative, so it will be 1. You understand it? Okay. Now, putting these values in A. So we get minus 4 into x1 is 1, minus 2 into x2 is also 1, plus x3 is 0, minus 2 into x4 is also 1, and minus x5 is also 1, is less than or equal to minus 3. So minus 4, minus 2, minus 6, and minus 2, minus 8, and minus 1, minus 9. Minus 9 less than or equal to minus 3, which is true. Okay? Now, we will find the values of x1, x2, x3, x4, and x5 in constraint B. In constraint B, x1, it is negative and it is less than or equal to, so x1 will be 1. x2, it is minus 2x2, so x2 will also be equal to 1. x3 is equal to, it is minus 4 into x3, so minus 4, it means that the sign is negative, so it will also be 1. x4 on the other hand and x5 both are positive and the constraint is less than or equal to, so x4 will be 0 and x5 will be 0. Now putting all these values in B, we get minus 4 into 1, minus 2 into 1, minus 4 into 1, plus 0, plus 2 into 0, less than or equal to minus 7. So minus 4 and minus 2 is equal to minus 6 and minus 4, minus 10. So minus 10 is less than or equal to minus 7, which is also true. Okay. Now we have got for this feasibility, for these values, we got both the values equal to true. It means that it satisfies both the constraint. These values satisfy both the constraint. So we will make a tree from this node. So here t is equal to 1, we make 2 branches. Okay, 2 and 3. Okay, and we can choose arbitrarily. We choose arbitrarily x1. We fix x1. Okay, we fix x1 for branching. Okay, we branched on x1 variable. You can choose x5, x4, x2, x3, and x1 arbitrarily. That is not kind of fixed procedure. Okay, but we go with the a kind of sequence. We will choose x1, then after that we will choose x2 whenever both of these constraints are made true. Okay, now at this point actually these are 2 branches, x1 is equal to 1 and x1 is equal to 0. Now at node 2 actually, okay, at node 2 we have fixed variable of x1 while free are x2, x3, x4 and x5. These 4 variables are free and x1 has a specific value which is 1 at node 2. Okay, so we are exploring node 2 over here. Now, similar, just we will repeat the process just like the first node 1, we will see the best completion. We know that x1 is equal to 1, which is fixed, and we will put all other equal to 0. Earlier, we also put x1 is equal to 0 in node 1. But here, as we have x1 is equal to 1 on node 2, we will put only the other 4 free variables equal to 0, and we will see if it is true for both the constraints. Okay. Now, putting values in A and B. So for A, what we get is minus 4 into 1, because here we already fixed it. Okay. And minus 2 into 0 plus 0 minus 2 into 0 minus 0 is less than or equal to minus 3, which implies that minus 4 is less than or equal to minus 3. So it is true for A. Now, for B, we have minus 4 into 1 minus 2 into 0 minus 4 into 0 plus 0 plus 2 into 0 less than or equal to minus 7. Implies that minus 4 is less than or equal to minus 7, which is not true. It means that it does not have any feasible solution at this best completion. Okay, so exploring, just like we explored the feasibility over here using the table, we will also use the table again, and we'll keep the x1 only fixed, and we will get the values of x2, x3, x4, and x5 for both A and B from the table. So we will explore the feasibility using the table. Now, x1 is equal to 1. This is fixed. Okay, we do not want to change this. This is fixed, but we need to find the value of x2, x3, x4, and x5 using this table and constraints. So the constraint is, the first constraint for A, x2 is equal to 1, because the sign is minus 2. Okay, x3 is equal to 0, x4 is equal to 1, and x5 is also equal to 1. So putting in A, we get minus 4 into 1. x1 is already 1, so it is fixed. Minus 2 into 1 plus 0 minus 2 into 1 minus 1 less than or equal to minus 3, which is equal to minus x minus 9 less than or equal to minus 3. So it is true. Now, for B, x1 is equal to 1, which is fixed. x2 is equal to, it will also be 1, because it is minus 2x2 in constraint. So it will be 1. You are understanding the, like I am writing the value of x2, x3, x4 using the table. You can draw the table and yes, I am understanding. But the thing is that the constraints are in front of me, so I can write it like you know mm, in seconds. But you need to write the constraints and this table. So we know that from the the start that it is less than or equal to. So it means that we are using the upper two values. This is less than or equal to, this is less than or equal to. Okay. So if this is negative, so it means that it is 1. It is negative 1. It is plus, so it is 0. Minus 2, it is 1. Minus 1, it is 1. It is like quick. You don't need to, think a lot about it when you have this table and this constraint. Or you have, it is in the Hillier book actually, in the Laborman book. I will send it to you. It is on article 9.7, implicit enumeration, in chapter 9, integer programming. Nothing will change actually. It will be same for both. Because you have only two values to consider, either 1 or 0. So you are looking for combinations and you are suggesting a value for some variable, you are fixing it. And then against that fixing, you want to find the values of another variable. You remember we did some problem, we had like 6 combinations and we find the values of all these combinations. It is same like, that, but that one didn't have branching, it has branching and, bounding. And regarding these values, these are quite easy. These are quite easy. You just need to, have the table and, look at the constraint. Just looking at the constraint, you will understand the value of it. You don't have to think about it. When you practice it, you will get it when you practice this problem. And maybe the problem is like for the three variables, or maybe it will not be like for 5 variables. So the tree will not be that long. It will like just one iteration or two iteration in the exam. Yes. So x2 is also 1 over here. I'm just looking at the constraint coefficient and I'm writing the values over here. It will also be 1. X4 is positive, so it will be 0. X5 is also positive, so it will be 0. Just like writing the values. I'm not thinking even about it, and I'm writing the values. So when you practice the problem, you will get it. Okay, now putting in B. Now B is minus 4. X1 is already 1, so we know that. Minus 2 into 1, minus 4 into 1, plus. So you see, here we have plus, so I wrote 0. Plus 2, so I will write this is 0. Less than or equal to minus 7. So minus 4, minus 2, minus 6, minus 10. So it implies that minus 10 is less than or equal to minus 7. So it is true. So it means that these values are true for both the variables, both the constraints, sorry. Okay. Now we will, make another tree. As it stands true for both of these, we will make another tree on 2, node 2. I will make another tree on node 2. For example, here I will make another tree here. This is t is equal to 1, node 1. This is x1 is equal to 1, x1 is equal to 0. This is 3. This is 2. And here, because it met all the condition, So we are making another tree. So we already have 3 nodes, so it will be fourth and it will be fifth. And here actually x2 is fixed, either 1 or it is 0. Now using LIFO, last in and first serve, yeah, first operate, okay, we will analyze 5 node. We will analyze this node, okay, based on LIFO. Because it is last, so we will analyze this, okay. Now if you see at this point, we have two fixed variables, x2 is equal to 0 and x1 is equal to 1. So the fixed are x1 and x2, and the free variables are x3, x4 and x5. Okay, now what we do is we find the best completion. We will repeat the same procedure for all the nodes. Okay, the best completion is, as we know that x1 is equal to 1 and x2 is equal to 0 at node 5. So these are fixed. Beside these, we put every other possible value equal to 0, and we will check it, put it in A and B to see if it stands true or it is